welcome to those who are joining, and welcome to those who watch this on a recording. As she said, I'm going to talk about the Institute for Terraforming Mars, which Earth and Mars, and I've given it an acronym ITEM or ITEM because you just can't have a project without an acronym these days. My co-author is Brad Blair, also of OrbChem, and he's got degrees in engineering, geology, mining engineering, and mineral economics. So he's got lots of terrific skills that are applicable to this field. My PhD's in inorganic chemistry, and I've had about 2 decades of experience or more in Mars and lunar ISRU chemistry at Pioneer Astronautics and the Kennedy Space Center. So I won't go through all this outline, but I'm going to talk a little bit about the current situation with Earth and its climate, and the causes, and then we'll skip to Mars as to the situation on Mars versus Terraform Mars. There's a couple of reference books I'd like to mention that you might want to look at, and talk quite a bit about terraforming and comparing technologies and so forth on, and then wrap things up. So Mars and Earth are very similar in a lot of ways, but they're also very different. So the Earth right now has too much carbon dioxide and it's getting hotter. Mars has too little CO2 in the atmosphere to keep the planet warm enough to be comfortable. It's very cold there. And Earth has a breathable atmosphere, and Mars has no atmosphere that's breathable, at least, a very thin carbon dioxide atmosphere. Earth gets about twice as much sunlight as Mars does. The population of Earth is almost 8 billion people, but Mars is 0, but maybe not for long. SpaceX is making great strides on sending people to Mars, and NASA has plans that are moving along to get people to Mars as well in the next decade after this one. But there's still a synergy in the technologies that are being looked at and used actually today on the Earth and planned for Mars that can help both planets. And ITEM is a concept for looking at this with a deliberate mind and coming up with ways that will do that sort of thing. So what's the Earth like now versus what it was in 1850, before the industrial age and pollution of the atmosphere began in earnest with fossil fuels primarily. So the gravity is the same as it was then. Atmospheric pressure is the same. But in the case of carbon dioxide, we've got around 50% more than we had way back when. A lot more methane and quite a bit more nitrous oxide. And back in 1850, there were no super greenhouse gases, which I abbreviate as SGGs. And now we've got about 250 parts per million. But global temperature was 13.7 degrees Celsius, and now it's about 15 degrees Celsius. So we've got a 1.3 degrees Celsius rise in temperature. And so let's move on. And just my view is blocked here, so I can't see what's under the right side of the screen. But just in general, we've seen large increases, as I just said, in the carbon dioxide and other gases that capture and that hold heat on Earth. Even in my lifetime. I was born in 1950, so I've lived through a lot of this. So this is a little redundant, but here's a plot of the temperature rise as a difference from the temperature back in the 1850s. And again, shows about a 1.3 degree rise. But notice how it looks like the curve is accelerating, and that's bad news. And carbon dioxide has a very long lifetime on Earth. And so we set that as a factor of 1 in terms of global warming potential. Methane has a much shorter lifetime, but it still has about 30 times as much ability as carbon dioxide to trap heat in the atmosphere. Nitrous oxide is we don't have very much of it, but it's a very strong greenhouse gas. And then the super greenhouse gases, which are primarily fluorinated gases that last anywhere from a few weeks to thousands of years, they will have an extreme effect. Even though we've got very little, they're very strong, like sulfur hexafluoride has 23,000 times as much global heating effect as carbon dioxide. So the conclusions for this are that Earth's getting hotter due to rising greenhouse gases from human civilization, and we are seeing lots of consequences of that. We get higher temperatures, stronger storms, polar ice melting, more extreme weather like extended droughts and drenching rain, and so we get forest fires and flooding. And some examples of that are California wildfires, Hurricane Katrina and others, Superstorm Sandy. Louisiana's been hit several times in a row, seems like, for the last few seasons by hurricanes. And had anybody ever heard of a derecho before this last couple of years? I hadn't. I had to look it up when I saw it in the news. It was this gigantic storm that flattened hundreds of square miles of corn in the Midwest. So what's Mars like today versus a terraformed Mars? Again, gravity's the same, but got a lot more atmosphere. So the current atmosphere is 95% carbon dioxide plus a significant amount of nitrogen and oxygen, and then small amounts of other gases. So in the future, once we partly terraform Mars, we'll have almost 100% carbon dioxide plus a little bit of nitrogen and argon, and then this small amounts of the super greenhouse gases that we add, like octafluoropropane. So we need a 4,000% increase in the mass of gaseous carbon dioxide in the Martian atmosphere. And we currently have an average temperature on Mars of minus 58 Celsius, and we want to get it up to 15 degrees Celsius, which is a change of 73 degrees Celsius. So we've got our work cut out for us. I'd like to mention a couple of textbooks in the area of terraforming. And I've got a copy of this one, Terraforming Engineering Planetary Environments. It's the first textbook in the field about terraforming. I recommend it, but highly, but the price has gone up a lot. I didn't realize I had a collector's edition worth about $200 used. But it is available on Amazon. Maybe your library has. There's a newer one that I haven't read yet called Terraforming the Creating of Habitable Worlds by Martin Beach. Came out in 2009. It's much more reasonably priced, $20 to $30 hard copy, or around $14 to $20 on Kindle. Has good reviews, and I'll be checking that out soon. So is it really possible to terraform Mars with current technologies? A couple of years ago, Bruce Jakosky at the University of Colorado used data from the Mars Maven orbiter, the Maven Mars orbiter, I'm sorry, to state that there's not enough carbon dioxide left on Mars to significantly raise the pressure there, that the carbon dioxide was lost eons ago due to erosion by solar wind and other forms of solar radiation. And hopefully you saw Chris McKay talk earlier today. He's at the NASA Ames Research Center, and Robert Zubrin of Pioneer Astronautics and the Mars Society. We all know him. They argue that Tchaikovsky is too pessimistic and that more data is needed from Mars's surface before we know that we can't terraform Mars. So we don't really know right now, but that's okay. We can still do things to develop the concept further and apply that knowledge to the Earth in some cases, and then look for more ways to apply Earth knowledge to terraform Mars. Standard, in quotations, excuse me, technologies that Chris talked about. He said, the orbiting solar reflectors or nuclear explosions are just not practical. They have to be huge, or you have to have so many, more than the world's nuclear arsenal in order to pull this off. But the idea is to warm the polar caps to vaporize the CO2. However, he did say that super greenhouse gases can be added to the atmosphere to cut down on the losses of infrared radiation from the surface. But the problem with that is that you need an industrial scale production system on Mars. Lots and lots of these big plants dedicated to making super greenhouse gases and emitting them into in the atmosphere there. There's also talk about crashing volatile bearing asteroids into the planet, and that way adding gases and greenhouse gases to the atmosphere. It takes hundreds of them, and so you're going to have stuff falling down on Mars for a long time and making a large explosions. So if you got people there, that would be quite hazardous. It's also expensive and slow because it takes a long time to move an asteroid around. Alternate technology, this is one that I talked about 3 years ago. So if you can make some things called self-replicating robots, that is robots that can make duplicates of themselves, and therefore you can have exponential growth in the numbers of these robots that are running the process. And then you also use a process called carbothermal reduction of regolith, which extracts oxygen from silicates, not just iron oxides in the soil, but the silicates themselves, which are the bulk of the regolith, the dirt on Mars. So you get oxygen out, and that process has been demonstrated on medium scale, let's say, on Earth. While I was at Kennedy Space Center, I was a NASA contact for that demonstration on Mauna Kea in 2009, I think it was. But you also get you'll also get iron, so you can use that to help make more robots, and water will be coming out, and then as well as any CO2 in the atmosphere. So you get multiple effects there. The biggest problem is you're going to have to mine half of the surface of Mars in order to get that much oxygen. And the oxygen works because it holds the heat longer. Mars atmosphere is so thin now that there's a significant greenhouse effect from just the existing carbon dioxide. It just irradiates away overnight, and you don't get net warming. But it's going to take a lot of power and a lot of robots. So let's compare other things. So if you've got Mars orbiting solar reflectors, you could, but again, I mentioned they're going to have to be too big to cool off the Earth. You could put a sun shield at the Earth-Sun L1 Lagrange point. And one way to do that is to ship an asteroid there and then fluff it up, so to speak, and spray the dust around so that it shields some of the sunlight and keep the Earth from getting too hot. One idea I came up with was maybe you can ship regolith from the moon using the hydrogen oxygen propellant from the polar water ice there, and spread that around at the L1 point. But I have not done the calculations to say how many launches you would do. It's going to take a lot. And we talked already about super greenhouse injection. On Earth, we want to remove carbon dioxide from the CO2 emitting sources like power plants and so forth, and directly from the atmosphere using amines or freezing. There's a photo on the left there of the largest CO2 capture plant on Earth that's just started recently operating in Iceland, and it captures CO2 directly from the air and sends it down underground into the salt formations, which will react with the CO2 and lock it away. And I also mentioned volatile bearing asteroid impacts. That's one thing we desperately want to avoid on Earth. We've got enough problems as it is. So you could also look at Mars technologies for making oxygen on Mars and so forth, like MOXIE, reverse water gas shift. So you can make you can convert the CO2 and oxygen and carbon monoxide. On the Earth, that could be quite useful. Again, an idea I came up with recently is to convert the CO2 into carbon monoxide and then react the carbon monoxide with itself to make CO2 and graphite carbon dust, which you could just lock away the carbon forever that way. And then I have some pictures of hardware related to this. And then cryogenic capture atmosphere on Mars to convert to methane and other hydrocarbons has been done on a lab scale. And you could do similar things on Earth. There's a couple of examples of what research for Mars has done that's been spun off into applications here on Earth. One is the Bloom Energy, which is a backup power system that runs off of natural gas and air and runs it through a fuel cell that generates electricity in case the regular power goes out. And there's a photograph there of this installation at Nokia in California, 400 kilowatts. That's a pretty significant power size there. And they're a $1 billion company. That got started back in the 90s, I believe it was, when K.R. Sridhar was doing work on making methane and oxygen using fuel cells. And at some point, we converted that into a commercial system, and they're doing quite well. Mike Heck talked about using MOXIE as well to make use natural gas and to make air to make electricity without combustion. Pioneer Astronautics spun off a company called Pioneer Energy quite a while ago. They used their expertise in that to look at ways to capture oil well emissions and convert them into valuable liquids, and avoiding and using the methane as well for power, so that you could monetize those instead of just burning it off. And there's a synthetic fuel plant in the Atacama Desert that's similar to these kinds of technologies that are being used, being developed for Mars, which is going to make gasoline for Porsches and other cars, because in a while they're going to be out of style. And they're down to $9 a gallon, which shows that it's becoming economical. So why are we doing this? Well, saving the civilization, I think that's a good idea. This is right now, Mars is a long way off physically, and years away before anybody can go there. But in large numbers, that's going to be a long time. So we got to fix the Earth. We got to keep the Earth functional and keep us alive. It's going to be very expensive to adapt, and a lot of people are going to have to move in order to get away from the rising oceans and seas. But exploring and settling Mars will create technologies that will be quite useful for the Earth. Maybe things like closed ecosystems for deserts and under the ocean to enlarge the area that people can inhabit. And we'll also, if we terraform Mars, we'll have a new branch of civilization that will go wild in terms of developing technologies that will be useful both for Mars and the Earth. And that will be our stepping stone to the stars. So what we're thinking about doing here at the item is to continue to evaluate this concept, since I just came up with it very recently. We're planning on writing a review paper to summarize all this that I've gone through and more, and talk to others who would like to get involved. And please contact me at tony@wordchem.space if you'd like to be involved in some way. Right now, we can't pay anything, but volunteers are welcome. So we've got some visions and mission and strategic plan, but I think I'm running a little bit out.
Yes,
So I won't go through all that. Just in terms of, we envision a future where the Earth has a stable and benevolent climate, and that Mars exploration will be well underway, and experiments will begin on Mars for terraforming. So we'll get ground truth, how much carbon dioxide is there. And we want to help make that vision a reality, and we'll build a knowledge base and look for ways to pay for it all. And let's see what's left. That's it. So it looks like we have a little time for questions.
Yes, thank you for this interesting lecture. And the first question came from Jack. How does water vapor compare as a greenhouse gas?
Well, it is a greenhouse gas, but I don't know I can't give you a quantitative answer there. I think it is significant. One of the problems is that as the Earth gets warmer, more and more, it can hold more water vapor in the air. And so that multiplies the greenhouse effect of the carbon dioxide and all the other gases that are a problem. I would think the same thing would happen on Mars as well. So it's not just the CO2. We would get benefits from having more and more water vapor in the atmosphere. Whereas on Earth, we need to stop rising and start bringing the concentration down of both.
The next question is from Dusty. Have you looked into algae-based sewage treatment projects? There's a brand new world first facility operating near him. But it's interesting. He is asking if you have looked into algae-based sewage treatment projects. Treatment projects.
No, I haven't heard of that, but that's I'll make a note of that. If it's a way of reducing carbon dioxide, I'm all for it. Does he say anything else about it?
And Michael says if temperature is increased to 73 degrees Fahrenheit and enough ingredients are added to increase the pressure to Earth-like pressures, Are there calculations that show that Mars can hold on to its new atmosphere?
Yes, as Chris McKay addressed it earlier today in his presentation, the calculations show that it could last around 100,000 years, maybe even longer. So it wouldn't be lost rapidly. It would be lost on a geological time scale rather than on a human time scale. 100,000 years ago on Earth, we're all still living in caves, so it's quite a different situation. So on civilization on Mars and people on Earth, I'm sure would want to help out with 100,000 years or less from now and figure out ways to hold on to that atmosphere or find ways to supplement it. Again, to them, moving asteroids around would be child's play. So you could just keep adding more and more. If if someone could come up with a way of creating an artificial magnetosphere around Mars that has very little a magnetic field on Mars. There's some local areas, but nothing globally. And so if there's some way to generate a magnetic field that would make that atmosphere last much, much longer, keep solar emissions from eroding it away.
Lutz Coleman is asking, how could nanotechnology, nanoparticles and aerosols be used for terraforming and to release from regolith and increase CO2 in the atmosphere? He's interested in collaborating and develop the research together. Okay,
well, personally, I don't know how to incorporate nanoparticles and so forth into this. That's an area that I really don't have any background in. But if there is someone, if you would like to get involved, get in touch with me. Like I said, Tony at orbchem.space.
And here's another question. Are all the compounds to generate super greenhouse gases like PFCs readily or readily available on Mars, or would it require most of the material to come from Earth?
Well, the basis for the super greenhouse gases would be the carbon dioxide that's already there. And there, I'm not sure where I saw this, but I just saw it recently that some of our robots on the surface of Mars, or maybe it was from orbit, have located compounds in the regolith, in some areas at least, that contain fluorine. There's plenty of chlorine there and perchlorates, but we're mostly interested in the fluorine, so we need to mine those areas on Mars that have those fluorine compounds, fluorine minerals, and then use the carbon dioxide there to make the greenhouse gases.
The next question is, Eric Bethke is asking that, if you could share again your email address, because you moved the slide so fast, but I can put it, meanwhile you give the other answer, I will put it in the chat. From Lutz Kuhlmann came excellent presentation, Tony, and to hear about item. Nitrogen is often one of the key missing ingredients for terraforming Mars. How do you envision and propose humanity and life introduce large quantities of nitrogen into the Martian atmosphere?
Well, it's not my idea, but I've read about using asteroids that contain ammonia and moving those into Mars as gently as you can. I guess you have to target them properly so that they don't hit something vital if you have a lot of people there. And then the ammonia would be released on impact. And then over time, the ammonia would be broken down by ultraviolet radiation and into nitrogen and hydrogen. The hydrogen would escape. So that could be done. It will take a lot of effort. Chris McKay talked this morning in his talk this morning said that just the CO2 atmosphere would be helpful. Like I said, just enough to you could not have to wear a spacesuit or pressure suit, but you would need oxygen. But over time, we could possibly add nitrogen, starting with ammonia from asteroids.